What's going on? What's going on? So, if you've been with me this far, which you haven't, but it's okay, you're here now, then you know that I went through I went through okay, I went through most of the fundamental beginner intro to Python and intermediate Python on Codecademy just now over like the past week or so. And this has all been in preparation for a series of internship interviews that I'm going to have in about 2 weeks' time. So now all of that was just preparation for this, which is me getting into Python for data structures and algorithms. This is what I'm really going to be tested on. And so I'm excited to get into it for real. And so let's just jump in. Learn data structures and algorithms with Python. Let's go. So, why data structures and algorithms? Learn what data structures and algorithms are, why they are useful, and how you can use them effectively. What even are data structures and algorithms? At the backbone of every program or piece of software are two entities, data and algorithms. Algorithms transform data into something a program can effectively use. Therefore, it is important to understand how to structure data so many algorithms can maintain, utilize, and iterate through data quickly. Data structures. Data structures are the way we are able to store and retrieve data. You're already familiar with Python lists and dictionaries, so you know that lists and arrays are sequential with data accessed by index, while dictionaries and objects use a named key to store and retrieve information. The data structures that exist in programming languages are pretty similar to real-world systems that we use outside of the digital sphere. Imagine that you go to the grocery store. At this particular grocery store, the frozen pizza is stored next to the bell peppers, and the toothbrushes are next to the milk. The store does not have signs that indicate where different items are located. In this disorganized grocery store, you would have a pretty difficult time trying to figure what you were looking for. Trying to find what you were looking for. Fortunately, most grocery stores have a clear order to the way the store is stocked and laid out. Similarly, data structures provide us with a way to organize information, including other data structures, in a digital space. How are data structures used? Data structures handle four main functions for us: inputting information, processing information, maintaining information, retrieving information. Inputting is largely concerned with how the data is received. What kind of information can be included? Will the new data be added to the beginning, end, or somewhere in the middle of the existing data? Does an existing point of data need to be updated or destroyed? Processing is about how data is manipulated in the data structure. This can occur concurrently or as a result of other processes that data structures handle. How does existing data that has been stored need to change to accommodate new, updated, or removed data? Maintaining is focused on how the data is organized within the structure. Which relationships need to be maintained between pieces of data? How much memory must the system allocate to accommodate the data? Retrieving is devoted to finding and returning the data that is stored in the structure. How can we access the information again? What steps does the data structure need to take to get the information back to us? Different types and use cases for data will be better suited to different manners of inputting, processing, storing, and retrieving. This is why we have several data structures to choose from, and the ability to create our own. Which data structure should I choose? Your plumber probably would not be the best professional to diagnose an illness, and your doctor probably wouldn't be the best person to do your taxes. They are each better suited for other tasks. Similarly, different data structures are better suited for different tasks. Choosing the wrong data structure can result in slow or unresponsive code and mess up your program. So it's important to consider a few factors as you make your decision. 1. What is the intended purpose for the data? Do any data structures have built-in functionality that is ideally suited for this purpose? Do you want to search, sort, or iterate data in a way in which certain data structures would be better suited than others? 2. Do you want or need control over how memory is set aside to store your data? Data structures that use static memory allocation, e.g. stacks or arrays, will manage memory for you and assume a fixed amount of memory upon instantiation with a cap on how much data may be added. Data structures that utilize dynamic memory allocation, e.g. heaps or linked lists, allow you to allocate and reallocate memory within the life of the program. While memory allocation is not something that you'll need to consider in languages like Python or JavaScript, these languages will manage memory for you, regardless of which data structure you use. It is something to bear in mind when working in other languages like C. 3. How long will it take different data structures to accomplish various tasks relative to other data structures? Technically, two data structures may both be able to accomplish the same task for you, but one may be quite a bit faster. This consideration, known as runtime, will be covered further in depth when you explore all the nifty tricks of asymptotic notation. Algorithms. Simply put, algorithms are instructions that the computer follows to carry out tasks. There are many types of algorithms, but some common ones that you will encounter in this course and likely the world are sorting algorithms, search algorithms, divide and conquer algorithms, greedy algorithms, brute force algorithms. How are algorithms used? Algorithms are used to manipulate and process data. Data structures are useful in maintaining and storing data, but algorithms are what actually utilize that data. Let's say we have a list of numbers. That list is the data structure that stores the numbers, but that's all it does. So let's say that again. Let's say we have a list of numbers. That list is the data structure that stores the numbers, but that's all it does. If we want to do something with those numbers, we need an algorithm. We could sort them using a sorting algorithm, or we could do something much simpler, like create a new list that contains the original list's elements multiplied by 2. Next steps. Now that you have a very broad overview of what data structures and algorithms are, let's dive into the specifics. In this course, you're going to create your data structures from scratch and then write algorithms that will utilize them. Our first data structure will be nodes, which are the foundation for many of the data structures that will follow. Let's get started. I'm excited. Nodes. Learn about the most basic building blocks of data structures. Nodes. What is a node? Nodes are the fundamental building blocks of many computer science data structures. They form the basis for linked lists, stacks, queues, trees, and more. In this article, we'll discuss what a node is, as well as how nodes link to other nodes. An individual node contains data and links to other nodes. Each data structure adds additional constraints or behavior to these features to create the desired structure. Consider the node depicted below. This node, node A, contains a piece of data, the number 5, and a link to another node, node B. Node implementations. The data contained within a node can be a variety of types, depending on the language you are using. In the previous example, it was an integer, the number 5, but it could be a string, 5, decimal, 5.1, an array, 534, or nothing, null. The link or links within the node are sometimes referred to as pointers. This is because they point to another node. Typically, data structures implement nodes with one or more links. If these links are null, it denotes that you have reached the end of the particular node or link path you were previously following. Again, typically, data structures implement nodes with one or more links. If these links are null, it denotes that you have reached the end of the particular node or link path you were previously following. A variety of node implementations are depicted in the following diagram. Examine the types of data and how some of the nodes are linked. Node implementations. What is the difference about node C? Why might that be useful? So node A has data 5 and a link to node B. Node B has data dog and a link null. Node C has data null and a link to node D and node E, where node D has data 55 and a link null, and node E has data 3 and a link null. Node F has the data cats and a link to node G. Node G has the data dog and a link back to node F. So to answer the question, what is the difference about node C? Why might that be useful? Node C itself doesn't contain any data, but it points to 2 other nodes. That might be useful because in order to get to node D and node E, we just need to have node C. Node linking. Often, due to the data structure, nodes may only be linked to a single other node. This makes it very important to consider how you implement modifying or removing nodes from a data structure. If you inadvertently remove the single link to a node, that node's data and any linked nodes could be lost to your application. When this happens to a node, it is called an orphaned node. Examine the nodes in the diagram. Node A has data duck and a link to node B. Node B has data duck and a link to node C, and node C has data goose and a link null. Okay, let's keep reading. Node C is only linked to node B. If you would like to remove node B but not node C, you can't simply delete the link from node A to node B. The most straightforward method to preserve node C would be to change the link in node A to point to node C instead of node B. However, some data structures may handle this in a different manner. Recap. Let's take a minute to review what we've covered about nodes in this article. Nodes contain data, which can be a variety of data types. They also contain links to other nodes. If a node has no links, or they are all null, you have reached the end of the path you were following. Nodes can be orphaned if there are no existing links to them. We good, right? We good? Check, we're good, streaming? Cool. I know I can do that because for some reason Codecademy takes a while to load. Nodes Python introduction. Now that you have an understanding of what nodes are, let's see one way they can be implemented using Python. Let me just real quick, I don't want to crap on Codecademy. I'm very appreciative, and it makes sense. It takes a while to load. I mean, it's loading up. I can run code in here. You know, have you tried Greater Than? That's what my school uses. This is much better than that. So anyway, we will use. I'm trying to get that Codecademy plug. Anyway, but I mean it though. Plug. We will use a basic node that contains data and one link to another node. The node's data will be specified when creating the node and immutable, can't be updated. The link will be optional at initialization and can be updated. Remember that at the end of a node path, the link to the next node is null because there are no more nodes left. In Python, this means it will be set to none. Begin by creating a new class, node. Let's do it. Add an init method in the node class. That takes a value. And an optional link node. Default should be none. These should be saved to the corresponding self properties. Self.value is value. Self.link node equals link node. Nice. Nodes Python getters. We need methods to access the data and link within the node. For this, we will use two getters, getValue and getLinkNode. These should each return their corresponding value on the self object. So def getValue self. They should each return their corresponding value on the self object. Implement the getValue getter in the node class. So define your getValue. This is where getters and setters. Come on, memory. Return self.value. Oops. Oh, colon. Nice. Implement the getLinkNode getter in the node class. Getter def get not fet get link node self return self dot link node. Nodes Python setter. We are only allowing the value of the node to be set upon creation. However, we want to allow updating the link of the node. For this, we will use a setter to modify the self.linkNode attribute. The method should be called setLinkNode. And should take link node as an argument. It should then update the self.linkNode attribute as appropriate. Implement the setLinkNode setter in the node class. Python nodes review. We have a few zany characters to keep track of, and Python nodes may do just the trick. Let's get started. Outside of node, instantiate 3 nodes. None have an argument for link node. The first has a value of likes to yak and be assigned to a variable Yakko. So Yakko equals node likes to yak. The second has a value of has a penchant for hoarding snacks and be assigned to Wacko. Wacko is a node. The value of has a penchant for hoarding snacks. The third has a value of enjoy spending time in movie lots and be assigned to Dot. Dot is a node and has a value of enjoys spending time in movie lots. Nice. Now, let's give these nodes some responsibilities. Yakko can keep track of Dot, and Dot can keep track of Wacko. Wacko can't keep track of anything though. Below the newly created nodes, use your setLinkNode method to give Yakko a link node of Dot and Dot a link node of Wacko. So, Yakko dot set link node, and Yakko has a link node of Dot. Dot set link node. So Dot, we're setting Dot's linked node to Wacko. Create 2 new variables, Dot's data and Wacko's data. Use both getter methods to get Dot's value from Yakko and get Wacko's value from Dot. Print Dot's data and Wacko's data to the console to see the results. So Dot's data is going to get value. Use both getter methods to get Dot's value from Yakko. So Dot's data dot get value. Use both getter methods to get Dot's value from Yakko. So we're getting Dot's value from Yakko. So Dot's data equals Yakko dot get value. And get Wacko's value from Dot. Wacko's data equals Dot get value, and then print Dot's data and print Wacko's data. Did you create a variable Dot's data and set it equal to Yakko.getLinkNode? I see. So Yakko is a node with the value likes to yak, Wacko is a node with has a value has a penchant for hoarding snacks, and Dot is a node with a value enjoys spending time in movie lots. Yakko's link node has been set to Dot, which means I wish I had something to draw. How do I draw? Drawer. Well, okay. Let's go to Pixlr. No, just create new. I just want to be able to draw, okay? Give me an art grid. And make it all white. Now, give me a brush. And we're going to put this right here. I'm really trying to cement this stuff in my brain, you know? This is important. This is very important. And I just closed it out, which goes to show you you're your own worst enemy. Let me view my history. And let me open this back up. I'm going to go ahead and put it right here. And this is unfortunate. It's very unfortunate. That's crazy, actually. This is why people don't use Pixlr, huh? Online Canvas. It's probably gonna bring me to Canva, huh? Or Sketch.io. Cool. Can I make the background white? I can, nice. Can I make the pencil? Let's go with yeah, I want a paintbrush. No, that looks crazy. I want a pen. And we're gonna make it fill in I was gonna say blue, but I don't want to put that energy out there, so I'm gonna go with green. Fill in green. Oh, what is this? What is that? That's crazy. No. Nah, what was that? Hold up. I don't even know what I'm looking at here. This is too much to handle. Can I just get... What is this? Am I stupid, or is this unnecessarily difficult? Probably both. No, probably the latter. Definitely the latter. So, I don't know what's happening here, but now I do. We're good. So, great. Let's separate these. Get rid of Pixlr, because how dare they want to charge me $1 a month or whatever it was. So we understand the data flow, right? This doesn't need to be too big. So we got a node right here. Goodness, my teacher does this stuff, and I think he's really bad at it. But now I'm realizing that it's not that easy to do this. But we have this node, Yakko, with some data. Yakko right now. We set Yakko.setLink node to Dot. So Yakko's pointing to Dot. Nice. Dot has some data. And we set Dot's setLink node to Wacko. So Dot is pointing to Wacko down here. And Wacko is pointing to none or null, but we're working with Python, so I'm gonna use none. Right now, what it's asking me to do is it's asking me to create two new variables: Dot's data and Wacko's data. Good enough. To use both getter methods to get Dot's value from Yakko and get Wacko's value from Dot. So we're trying to get this from this. And we're going to do that with, or we're also trying to get this from this. How are we going to do that? How would you get Yakko's value? So right now, where is Yakko's value at? Yakko's value is in Yakko, the node which is assigned to Yakko. Yakko's linked node is dot. If we do Yakko dot, well, we already know the answer, but let's think about it because we know the answer. So Yakko dot get link node. So we're getting Yakko's linked node. So we're saying, what is this thing linked to? Oh, it's linked to dot. So we're going to get its linked node. I don't know how to do this, but you're hearing my voice, right? So we're looking at this, looking at that. Don't just listen to me. We're looking at this and we're saying, where do you point to? Oh, you're pointing to dot? Oh, nice. So Yakko.getLink node. Now we're at dot. Now we can run our get the value and we can store it up in dot data. Similarly, we have this Wacko's data variable and we want to get Wacko's value, but we can't look directly at Wacko, so we're gonna look at dot first. We're gonna look at this thing. We know dot is pointing to Wacko, so we're gonna say we know dot's linked node is Wacko, so we're gonna do get linked node. Listen to my voice again. Listen to the voice. Don't try to read whatever that says. We're gonna look at this, and that's gonna bring us right to Wacko. Wacko has a value of none. We're gonna go ahead and store that in Wacko's data. Make sense? Hope it does. So the idea being, we create this class node. We do this dunder init with a self, obviously, because you need a self for every method within a class, and then value, and then link node, which defaults to none. Self.value is value. Self.link node is link node. Another method, set link node, which takes in self and takes in a link node. Self.link node equals link node. Another method, get link node, self returns self.link node. So if you run set link node and you pass it something, that node that you pass it is now the linked node of this class object, of this node class object. If you run get link node, you're gonna get returned whatever the link node of the object is. And if you run get value, you're gonna get back the value of whatever the object is. So let's be very simple here. When we initialize Yakko as an object of the node class, as an instantiation of a node object, right? And we add in a value of likes to yak. So now Yakko's value is likes to yak. If we run Yakko.getValue, it's going to return back to us likes to yak. If we run Yakko.setLinkNode, whatever we enter in it becomes the linked node of Yakko. And so if we do Yakko.getLinkNode, since we entered in dot for the link node of Yakko, Yakko.getLinkNode is going to return dot. So if we want to get dot's value and store it in dot's data, beyond just Yakko.getLinkNode, now we're at dot. If we add a .getValue, we're getting the value that we've stored in dot, which is enjoys spending time in movie lots. So we're building a path. We don't have to get dot's data directly from dot because Yakko points to dot. Yakko's linked node is dot. So if we get Yakko's linked node, we can get the value of Yakko's linked node, and that is dot's value. That's the idea here, is that data structures allow us to look at where this node is pointing, and by looking at what this node points to, get to this other node that we want to observe or handle or process for some reason. So now dot to get Wacko's data, since we know that dot is pointing to Wacko, dot's linked node is Wacko. Wacko's data can be retrieved by assigning it to dot get link node dot get value. And now we've gotten the value of Wacko, which is none, and we stored it in Wacko's data, and we can run this, and we can see here that dot's data is that dot enjoys spending time in movie lots. Wacko's data is that Wacko has a penchant for hoarding snacks. And now what I've remembered, right? This is important because this is learning happening. Where's my eraser? What is happening? You don't have an eraser easily accessible? This is crazy. Really? This is not on me. This user interface could be much better. There is no easily available eraser. You have to come in here. That's crazy. Okay. So, oh my goodness. Okay. I'm not gonna lose my crap. You know what? This is the internet. I'm not gonna lose my shit. What I'm gonna do is I'm gonna come here. I'm gonna go ahead and I'm gonna grab a streamer. I don't know what this does, but I like its name. I'm gonna go ahead, click white, and I'm gonna stream that out. Stream that like I'm streaming now. I'm a streamer. I feel like Bob Ross. Just, stream it out. So I know I got confusing with the arrows here, but the idea is back to the pencil, back to green. Goodness gracious. Let me zoom out. How do I zoom out? Okay. No. Right there. But Wacko does have some data, so let me not make it confusing. At least not more confusing than I've made it. But we got through this, and I've spent sufficiently 20 minutes on it or whatever. So let's go to the next one. And I don't even know. How do I clear this? Just get out of here. Consider the following nodes and links. A points to N points to T. If you want to remove node N, but preserve node T, what are the steps you would take? Remove the link on N using n.setLink node none. Incorrect. Because then you've deleted T. T is orphaned now. We don't know where how do we get to T? We want to remove node N. So we're going to change the link on A to point to T using a.setLink node T. Correct. Which two features do most nodes contain? Data and links to other nodes. Consider the following nodes and links. A points to N points to T. If you want to remove node N but preserve node T, what should the resulting structure look like? A points to T. Right there. A node containing only null pointers indicates what? You are at the end of the node path you were following. Which of the following methods implemented in the node class are required to establish a node class with an accessible but immutable value? I'm going to go ahead and say with an accessible but immutable value. Which of the following methods implemented in the node class are required to establish a node class with an accessible but immutable value? So obviously they all start with dunder init. To establish a node class with an accessible but immutable value. Dunder init get value. So you're grabbing out the value, and what we're trying to do, big picture, is we're trying to, which of the following methods implemented in the node class, we're trying to establish a node class with an accessible but immutable value. So we get the value, which returns the value of it to us. We get the link node, we set the value, and we set the link node. or we could get the link node and set the link node, and that's incorrect, probably. Or we could get the value, get the link node. So this is its value. This is its link node. We're gonna set its link node. I don't know. That doesn't sound right to me. And it get value, got the value, get the link node, got the link node. We're gonna set the link node, put it over there, point to that, and increment the value. That doesn't sound right because we're trying to establish a node class with an accessible but immutable value. To establish a node class with an accessible but immutable value. Well, immutable means you can't change it. So set value doesn't sound like it should be in the equation. So I'm gonna go ahead with init get value, get link node, set link node. Sounds right to me. And it is right. Because I'm right. I don't know why I'm turned up. It's because it's a new course. There's something refreshing about not taking intermediate Python anymore, because it just got boring. This is new, it's fresh, and this information really sinking in my brain might get me a dope internship. So, I'm gonna make it stick. Linked lists, conceptual. A conceptual overview of linked lists. What is a linked list? Linked lists are one of the basic data structures used in computer science. They have many direct applications and serve as the foundation for more complex data structures. Linked lists. Can you think of a real-world example using bidirectional links? Node data, link pointing there, node data link to pointing there with a node data link. It makes me think of like a website, right? I go to Google. This right here, this is the Google search engine. I put in some data and it links me to a page which has a bunch of data, and I go click on this link, which brings me to a website which has some data and some other links to some other websites or web pages or what have you. That's what I think of. The list is comprised of a series of nodes as shown in the diagram above. The head node is the node at the beginning of the list. The list is terminated when a node's link is null. Null over here. This last node is called the tail node. Consider a one-way air travel itinerary. The trip could involve traveling through several airports or nodes connected by air travel segments, links. In this example, the initial departure city is the head node, and the final arrival city, after a little layover, you finally get to the final arrival city, that's the tail node. Since the nodes use links to denote the next node in the sequence, the nodes are not required to be sequentially located in memory. So you could think about it like, just because I'm going from Boston to let's say Chicago, doesn't mean I'm going to fly sequentially. Doesn't mean I'm going to fly straight from Boston straight to Chicago, because I might be broke, which means I might need to get a layover in Washington, D.C. for some reason, which means I'm not going from Boston to Chicago. I'm going from Boston to D.C. to Chicago. So by that logic, and since we're thinking about these cities, airports as nodes, and the air travel segments, or just the plane rides, because I don't know why they use that big word segments. We're thinking about the plane rides as the links. Since the nodes use links to denote the next node in the sequence, the nodes are not required to be sequentially located in memory. These links also allow for quick insertion and removal of nodes, as you will see in future exercises. So the sequential located memory thing is like, if you think about a list or an array, so I don't want to use the word list because this is a linked list, but think about an array, right? Or a list in Python, right? If I put some square brackets and I do 1, 3, 8, those are all next to each other sequentially in memory. I could look up the memory location of the list, and that's going to bring me to the location in my computer's memory where that 1 exists. And if I look at the direct next location in memory, I'm going to see that 3. If I look at the direct next location in memory, I'm going to see that 8. And then if I look at the direct next location, I believe I'm going to see a null or a none, or it's a null. However, that's with a traditional list. That's with an array. With a linked list, if I go look up the memory location of my head node, it doesn't mean that the next, memory location in my computer's memory is going to be the next node in my linked list. Because no, that's not how it works. We don't need to do that with a linked list. If I go look at the head node, that node has data in it, but it also has a link. And it could let me know that the next member in my linked list isn't sequential. It's not right next to me. It's way over there, but I'm pointing to it. So cool. From here, I can go point over to I don't want to go out of the crop, but I can go over here. And you know what? My next member in this linked list isn't right here. I'm pointing over here, right here. And so our linked list doesn't have to live sequentially in memory, in the computer's memory. Each node points to where the next member of the linked list is. And when I get to this over here and it doesn't have a pointer, it's pointing to null, it means I'm at the end. This was a 3-part linked list. So these links also allow for quick insertion and removal of nodes, as you will see in future exercises. Common operations on a linked list may include adding nodes, removing nodes, finding a node, traversing or traveling through the linked list. As an example, we added values to the linked list diagram from above. So node A has data cats and it links to node B. Node B has data dogs and it links to node C. Node C has data birds and its link is null. It links to nothing. This linked list contains 3 nodes, node A, node B, and node C. Each node in this particular list contains a string as its data. As the sequence is defined, the order is cats, dogs, and birds. The list ends at node C, since the link within that node is set to null. Adding to and removing from the linked list. With linked lists, because nodes are linked to from only, because nodes are linked to from only one other node, you can't just go adding and removing nodes willy-nilly without doing a bit of maintenance. Adding a new node. Adding a new node to the beginning of the list requires you to link your new node. So I got this new node over here. I'm going to link it to the current head node. This way, you maintain your connection with the following nodes in the list. Removing a node. If you accidentally remove the single link to a node, that node's data and any following nodes could be lost to your application, leaving you with orphan nodes. If I just accidentally remove this node B over here with my dog in it, that dog is gone. Not only is that dog gone, but the birds are gone too. How am I supposed to know how to get to birds if I don't have the pointer from dog? All I have now is cats and it's pointing to nothing now because dogs is gone. Dogs is gone. To properly maintain the list when removing a node from the middle of a linked list, you need to be sure to adjust the link on the previous node so that it points to the following node. So if I want to remove dogs, I don't just get dogs out of here. I just adjust the pointer of cats node, this node A with the data cats in it. Now it's pointing to birds, node C. And now dogs is gone. But our list still has a structure and we didn't lose node C, we didn't orphan node C just because we had to get rid of the dogs. Sometimes you got to get rid of the dogs, but you still want to keep the birds, you know? Depending on the language, nodes that are not referenced are removed automatically. Removing a node is equivalent to removing all references to the node. So again, depending on the language, nodes that are not referenced are removed automatically. Removing a node is equivalent to removing all references to the node. Look at the diagram below to see the proper manner of removing a node. Node A, data duck, links to node B, which has data duck, which links to node C, which has data goose, which has a null link. Here next we see node A, data duck. We're going to make it link to node C. Node B has data duck and also links to node C. Node C has data goose and its link is still null. Next we see node A has data duck and links to node C. We've orphaned node B now. And so the proper manner of removing the node, now that we've orphaned node B, our linked list is now just node A with data duck and it's linking to node C, which has data goose and links to null. In order to remove node B, you must first link node A to node C, where node B was linking. Then you can remove node B. Review. Let's take a minute to review what we've covered about linked lists in this lesson. Linked lists are comprised of nodes. The nodes contain a link to the next node and also the previous node for bidirectional linked lists. Can be unidirectional or bidirectional. Are a basic data structure and form the basis for many other data structures. Have a single head node which serves as the first node in the list. Requires some maintenance in order to add or remove nodes. The methods we used are an example and depend on the exact use case and or programming language being used. Nice. What's next? Node implementation. Let's implement a linked list in Python. As you might recall, each linked list is a sequential chain of nodes. So before we start building out the linked list itself, we want to build up a node class in Python that we can use to build our data containers. Remember that a node contains two elements: data, a link to the next node. Ready? Let's get started. Because the workspace is set up with spaces instead of tabs, you will need to use spaces to prevent Python from throwing an error. You can learn more about this here. I hate using spaces, but okay. Def. Sorry, no. Not creating a method. Getting class. Node. Within script.py in the pane to the right, create an empty node class. Done. Inside, define an init method for the node. Def dunder init self. It should take a value and a next node. So self value next node self dot value equals value self dot next node equals next node. Next node should default to none if not provided. Next node equals none. These variables should be saved to self with corresponding key names. Run it. Define get value and get next node methods. These should return the corresponding values from self. So def get value self return self dot value. Def get next node self return self dot next node. Oops. There we go. Define a set next node method that takes a self and next node as parameters and allows you to update the link to the next node. I've been using tabs, haven't I? I don't even know. Well, we'll see if it runs. Def set next node, which takes in a self and a next node. Self dot next node. Goodness gracious. Goodness. There we go. Self dot next node equals next node. So we defined a set next node method that takes a self and next node as parameters and allows you to update the link to the next node. Got you. Outside the node class, create an instance of node called myNode. MyNode equals node, the value of 44. Use get value to print the value of my node. Print my node, not my nodes, my node dot get value. Boom. Next, linked list implementation 2. With the node in hand, we can start building the actual linked list. Depending on the end use of the linked list, a variety of methods can be defined. For our use, we want to be able to get the head node of the list. It's like peeking at the first item in line. Add a new node to the beginning of the list. Print out the list values in order. Remove a node that has a particular value. Let us get started. and again, no tabs, just use spaces. Within script.py, in the pane to the right, create an empty linked list. So create an empty linked list class. So class linked list. Def init self. We want to be able to instantiate, so define an init method for the linked list. We want to be able to instantiate a linked list with a head node. So init should take a value as an argument. Make sure value defaults to none if no value is provided. Self.value equals value. Inside the init method, set self.headNode equal to a new node with value as its value. Okay, that makes sense. Self.head node equals value is a new node with value as its value. I see now. I see, said the blind man. Boom. So we created a class called linked list, which initializes with a value which defaults to none, but you can pass it a value. And if you do pass it a value, then self.headNode is a class variable we're creating called headNode of this linked list, and its value is a node where we're passing the value that we entered into the argument of our linked list. We're passing that value directly to a new node object. And so now our head node, if we do linked list 4, we've created a new head node with the value 4. Amazing. Define a get head node method. So again, no tabs, def get head get head node self. That helps us peek at the first node in the list. Return self dot head node. Inside the method, return the head node of the linked list. Cool. Linked list implementation dos. So far we can create a new linked list using our dunder init method, get the head node of the linked list using .getHeadNode. Next up, we'll define methods for our linked list class that allow us to insert a new head node, return all the nodes in the list as a string so we can print them out in the terminal. Define an insert beginning method which takes new value as an argument. So add your insert beginning and stringify list methods below. So again, I hit tab again, so no tab. Define an insert beginning method which takes new value as an argument. So def insert beginning self new value. Inside the method, instantiate a node with new value. So name this new node. So new node equals node new value. Inside the method, instantiate a node with new value. Name this new node. Done that. Now link new node to the existing head node. Self.head node equals new node. Finally, replace the current head node with new node. Oh, I see. What I need to do, right? We got this set next node up here. We got this method. Our nodes can set the next node. And what this is telling us to do is to link new node to the existing head node. So we need to take our new node and link it to the existing head node, which we can do by doing new node dot set next node, goodness, set next node, self dot head node. Did I do that correctly? I believe I did. And now what I can do is I can do self dot head node equals new node. Note, because the workspace is set up with spaces instead of tabs, you need to use spaces. Did I do that right? I think I did. So again, what we're doing, right? To insert beginning, our insert beginning method of our linked list class, it takes in a new value. So let's say let's cement it in, right? Let's really get it in our heads. Get this out of here. I didn't think I'd have to see you again. How do I just go away? Cool. So I'm gonna click this pencil right here. I'm still rocking with green. I don't want to do that. What I wanted to do was that. Get that out of here. So just to really lock it in, right? We get it. I know you get it, I get it, but let's lock it in. So what we're gonna do, right? We got this linked list class and we got this insert beginning method of our linked list class, which takes in a value. So we have, this is our linked list. Actually, no, this is our linked list, right? Not sequential, not sequential. That's our linked list. This is all our linked list. Goodness, it's pretty good. That's the linked list. Adding, we have this new value that we just brought to the table. I don't know why I'm doing this, because it's fun. That's why I'm doing it. But we just brought this to the table. So now what we do, right? If we want to add this and we want to insert it to the beginning. So we already did this, new node equals new node with this value. And new node dot set next node, boom, its next node is this. And now what we do, this was the head node, this was the big honcho. This did have the head crown, but we said nah, no mas, no more. Can I zoom in? It's a little bit too zoomed. I'll zoom in. Too zoomed again. Click on that. Click on that. Gone. No more. That doesn't have the head. I messed that up by making it too scribbled, so I'm gonna go grab this color. Now that got the head. That's got the H. That means that is the head. Self.head node equals new node. Cool. So let's get that out of here. Next up, we're gonna define a stringify list method we can use to print out a string representation of a list node values. The method should traverse the list beginning at the head node and collect each node's value in a string. Once the end of the list has been reached, the method should return the string. You can use string to convert integers to strings. Be sure to add a new line between values so that each value prints on a new line. So here we go. Def stringify value self print out a string representation of a list node value. So for node in see, the way I'm thinking about this, right? We're gonna start with self. We know we have self.head node. So our string equals self.head node. That would give us whatever just the value of our head node is. But we don't just want that. What we want is to print out a string representation of a list, all the list node values. So start with the head node. if the current node links to another node, move to its link and store its value in string. So if head node, if self dot head node, I don't think I need to do that. Self dot head node dot get next node, yeah, dot get next node, so if that exists, right? So if self dot head node dot get next node, not sure I'm doing this right, but trial and error, right? If self dot get node dot get next node, so what I'm trying to say is, like, if that evaluates to anything that's not 0 or null, string plus equals new line, string plus equals string self dot head node dot get next node dot get value. So I'm gonna make this while. So the current node links to another node. So while self dot head node dot get next node, string plus equals new line, string plus equals string self dot head node dot get next node dot get value. That's gonna continue until self dot head node dot get next node is a null. So here we're just gonna do this. String just is initialized as an empty string. So initialize an empty string. While the current node links to another node, while self dot head node dot next initialize an empty string, init a current node as the head node. So current node equals self dot head node, while current node dot get next node, string new line, or what we'll do is string plus equals current node, right? Here's when we'll do a do while loop, right? It's gonna be crazy if all this is very unnecessary, but whatever. Do. I don't know why that's orange. Can you do whiles in Python? Goodness. I guess I'll use if. If current node dot get next node, string plus equals current node. So if the current node has a next node, we add the current node, we add a new line, and then current node equals current node dot get next node. Boom. The only thing here is this is not going to work for our last node. That's why I wanted to use a do while loop. So while the current node links to another node, while current node dot get next node, string plus equals current node, new line, move its link and store its value in a string. Whatever, I did that. Get that out of here. So the way I'm thinking about this right now, and I know I'm going at a snail's pace, but you know what? I need to learn, right? Unfortunately, I'm taking a data structures and algorithms class, and unfortunately, the teacher, look, some people say learning styles aren't a thing. Why can't I access my sidebar? Some people say learning styles aren't a thing. I think that maybe that's true, but teaching styles are a thing. And sometimes the way a teacher decides to teach doesn't really gel with the way I prefer to learn. Why is technology failing me? There we go. Now, let me select this. What did I do? All right, this is actually crazy. I've had enough. What is happening? I actually don't know. I think my tech is just breaking. This is a new Mac Mini. I paid money for this. Money that I don't have anymore. Best Buy has it. Actually, the Apple Store has it. Best Buy has the money for this, not this, for this camera, for this curved 34-inch display. I'm not going to just start flexing my tech, but I'm just bored because it's like, why is this failing me? Come on, man. Come on, man. All right, cool. All right. I guess let's quit this then, huh? It's still going? 1 2 1 2. Still going. Yeah, my friend told me to get this Arc browser. But it's kind of buggy, but it looks cool, right? Like I could do all this side by side tabular stuff. It's kind of buggy though. Anyway, back here. Let me not draw. I don't need to draw. I need to think with my brain. For once, let's see. This is taking too long. Define a stringify list. First of all, I didn't even name it right. Def stringify list method we can use to print out a string representation of a list node's values. The method should traverse the list beginning at the head node and collect each node's value in a string. So I can't just do for node and linked list, right? Because all we have is the head node. We don't know how many nodes are in the linked list. So we start at the current node. So the reason I'm having trouble kind of conceptualizing this, we start at the current node. So I can't use a for loop. Can I use a while loop? So while current node dot get next node is working, we're gonna add the current node. We're gonna to the string. We're gonna add its value to the string actually. We're gonna add a new line. And we're gonna go to the next node. So now the loop starts to go over again. Say we have this node, while it's pointing to something, add this value to the string, add a new line to the string, and then go to the next node. Does this point to something? See, the issue is if it doesn't point to something, then our list doesn't start. I mean, our loop doesn't start. That's why I need a do while loop. How do I do a do while loop in Python? Should have started here, honestly. How I do a do while loop in Python. Does not have a built-in do while loop, but you can simulate one using a while loop. So while true. Why doesn't Python have a do while loop? Alright, whatever. So that's what messed me up. And this is what messed me up. This is another tangent, but I did a mock interview, right, recently. And I did poorly by my own estimation and by anybody's estimation. I did poorly because I just kept getting my syntax confused. Right now I'm taking a C++ class in school, a Java class in school. I'm building a website for a business in JavaScript, and I use Python for fun. I shouldn't say for fun, but like for personal projects. So I guess you could call it for fun. It hasn't been that fun recently because now my mindset isn't tinkering and hacking and stuff. My mind is getting my schoolwork done. My mind is working on this business's website, and my mind is preparing for these interviews. But all in all, Python is like my go-to language of choice if I can only pick one. And I'm on a desert island. I have nothing but one language. I'm picking Python personally. So given that, what was my point? Oh yeah, I was doing the mock interview and I chose to do it in Python, and I just kept getting my syntax wrong. That's why I'm doing this right now. I couldn't even make a class because I was defining a class like one would in C++. And actually I was stuck in analysis paralysis because I forgot what syntax to use to even define a class in Python. Never again. So this doesn't feel like it's probably the way that this wants me to do it, since Python doesn't have a built-in do while loop, but I'm gonna brute force it and then see what it would say. But I want to get it to work first. So while true, string plus equals string current node dot get value. I don't know what I was thinking before. So string plus equals string current node dot get value. String plus equals new line. Current node equals current node dot get next node. And then how do we end it? If not condition break. If current node dot get next node if not current node dot get next node, or I should say if current node, I'll say I'm gonna be fancy with it, if not current node. Actually no, I don't think that's right syntax. If current node is none, break them. So now define a stringify list. We've done that we can use to print out a string representation of a list node's values. The method should traverse the list beginning at the head node and collect each node's value in a string. Once the end of the list has been reached, the method should return the string. Return string. You can use string to convert integers to strings. Be sure to add new line. Let's run it. Bam. Boom, bam, bizzle. Let's see what it would have said to do. Inside your stringify list method body, start with a variable set to an empty string to collect all of the node values. We did that. You can use a while loop and nodes dot next node method. There's a dot next node method. A get next node. Yeah. To traverse the list, if you accidentally get stuck in an infinite while loop, just use your browser to reload the page before editing your code. So I did what was right. It just took me a little bit, but that's how you learn. That's how you learn. While true, string plus equals string current node dot get value. String plus equals new line. Current node equals current node dot get next node. If current node is none, return string. Test your code by uncommenting the print statement at the bottom of script pi. Uncomment that. Did your list print what you expected? So our linked list is 5, so we're sending 5 here. So we just have one node with a value of 5. So we should just get 5 new line. Yeah. If we, Did you uncomment the print statement? Not yet. I'll get there. Or I did, but if we do ll.insert beginning 70, so now our linked list should print out 70 and 5. If we uncomment ll.insert beginning 5675, we're going to get that at the beginning of our linked list, now won't we? And if we uncomment that, we're going to get the 90 at the beginning of the linked list. I'm a coding genius. Uh-oh. This one seems like a tough one. I don't know, but it's a 3 and it's got 26 minutes. Let's do it though. Linked list implementation 3. Nice. Now we have a bunch of helpful linked list methods under our belt. The final use case we mentioned was the ability to remove an arbitrary node with a particular value. This is slightly more complex, since a couple of special cases need to be handled. Consider the following list. A points to B points to C. If node B is removed from the list, the new list should be A points to C. We need to update the link within the A node to match what B was pointing to prior to removing it from the linked list. Lucky for us, in Python, nodes which are not referenced will be removed for us automatically. If we take care of the references, B will be removed for us in a process called garbage collection. So again, we need to update the link within the A node to match what B was pointing to prior to removing it from the linked list. But lucky for us, in Python, nodes which are not referenced will be removed for us automatically. If we take care of the references, B will be removed for us in a process called garbage collection. For the purposes of this lesson, we'll create a function that removes the first node that contains a particular value. However, you could also build this function to remove nodes by index, or remove all nodes that contain a particular value. At the bottom of script.py, add a remove node method to linked list. It should take value to remove as a parameter. We'll be looking for a node with this value to remove. In the body of remove node, set a new variable current node equal to the head node of the list, self.headNode. We'll use current node to keep track of the node we are currently looking at as we traverse the list. Still inside the method body, use an if statement to check whether the list's head node has a value that is the same value as value to remove. If current node is equal to value to remove. If it does, we found the node we're looking for, and we need to adjust the list pointer to head node. Inside the if clause, set self.headNode equal to the second node in the linked list. So if current node is equal to the value to remove, set self.headNode equal to the second node in the list. Current node dot next or get next node What'd I do wrong? Does your if case set head node to the second node in the list? Self.headNode equals current node dot get next node. I thought it did. I'm just guessing. Don't guess. Don't guess. Interesting to see how they did that while loop up there, though. They did while current node. If current node dot get value is not equal to none. String list plus equals string current node dot get value plus new line current node equals current node dot get next node return string list. It's a much better loop, but hey, I made one too. Wasn't pretty, but it worked. Okay, focus. Still inside the method body, use an if statement to check whether the list head node has a value that is the same as value to remove. So we did current node equals self.head node. If current node is equal to value to remove, current set the next node to the current node. Is that what it wants me to do? Does your if case set head node to the second node in the list? I thought it did. Maybe self dot head node dot set next node does your if statement set head node to the second node in the list. Self dot head node dot set the next node of our head node. And we're going to make the head node the next node of the head node. Inside the set self.head node equal to the second node in the linked list. So let's take it line by line, right? Use an if statement to check whether the list head node has a value. Same as value to remove. If head node is equal to value to remove. Goodness. So let's make it easy here, right? Self.head node is equal to value to remove. If it does, we found the node we're looking for, and we'll need to adjust the list pointer. We found the node we're looking for. Adjust the list's pointer to head node. So the whole idea of what we're doing we're creating a function that removes the first node that contains a particular value. What we did in the last step is we added this remove node function or method to our linked list class. It takes a value to remove as a parameter. We're looking for a node with this value to remove. In the body of remove node, we set a new variable current node equal to the head node of the list. So current node equals self.head node. Is that right? I mean, it's got to be right. It told us we were right. You can retrieve head node using the get head node. Maybe it's not right. But that confuses me. In the body of remove node, set a new variable current node equal to the head node of the list. I think it's right. The self.head node should give us the same thing as self.get head node. So I think we're good there. Still inside the method body, use an if statement to check whether the list head node has a value that is the same as value to remove. So if self.head node is equal to value to remove, if it does, we found the node we're looking for. Adjust the list pointer, the list's pointer to head node. This is where I'm confused, because if we're traversing a list, so let's assume the head node is the value we're looking for. We're looking for 4, and the head node has a value of 4. If self.head node is equal to the list head node has a value. Oh, I see. If self.head node dot get value is equal to the value to remove, then we found the node we're looking for. Adjust the list pointer to head node. So if this is the value we're looking for, found the node we're looking for, and we need to adjust the list's pointer to head node. Inside the if clause, set self.head node equal to the second node in the linked list. So if self.head node is the value we're looking to remove, inside this clause, set self.head node equal, so self.head node equals self.head node dot get next node. Boom. Add an else clause within the else clause. So else, add an else clause within the else clause, traverse the list. Let's write this, let's pseudo-code it up. Imagine if I talk this way in my interviews. But the idea is you're supposed to talk, right? They want somebody on their team who be a team player, be cool. Anyway, traverse the list. Until current node dot get next node dot get value is the value of the node to remove. Until current node dot get next node, until the current node's next node has a value equal to value to remove. So I'll say while, so else, oops, why did I make a capital? Else, while current node that next node dot get value is not equal to value to remove. Current node equals current node dot get next node. So while our current nodes, so if the first node doesn't have a value equal to the value we're looking to remove, then while the current node's next node has a value that isn't equal to the value to remove, then current node equals the current node dot get next node. Does this, okay, that makes sense. When value to remove is found, adjust the links while that. So okay, current node equals get next node, that, and then while, so current node dot get next node dot get value is not equal to, oh, but it is now. So now we're gonna do something else. So let me go to that. When value to remove is found, so that will be here. We'll exit this while loop. Adjust the links in the list. Adjust the links in the list so that current node just the links in the list so that current node is linked to next node dot get next node. where do we define next node? Next node is a value that can be accepted by node, but that's not how we're trying to use it here. Adjust the links so that when the value remove is found, so we're here. If we exited the while loop, the value remove is found, and it is current node.get next node.get value. So current node equals current node.next node. Wow, so we're gonna check is current nodes get next node the value we're looking for. It is. So now what we're gonna do is adjust the links in the list so that current node is linked to skip over this one and go to the next one. Current node dot set next node equals current node dot get next node dot get next node after you remove the node with a value of value to remove. So when value to remove is found, adjust the links in the list so that current node is linked to next node dot get next node. After you remove the node with the value of value to remove, make sure to set current node to none so that you exit the loop. I didn't think we were in a loop anymore. Real quick, I thought we were good. We're not. Invalid syntax. Again, while current node is not equal. Oh, did I not put underscores? I did not put underscores. I'm crazy. Does your else case traverse the list and remove the node with a value to remove? Current node dot set next node equals current node dot get next node dot get next node. After you remove the node with the value to remove, make sure to set current node to none so you can exit the loop. Does your else case traverse the list and remove the node with a value to remove? So let's think about this. Current node equals self.head node. So we're at the head. Let's say we have two nodes in the list. We're at the head node, right? If self.head node.get value is the value to remove, self.head node equals self.head node.get next node. So this is now the head node, but that's not the case here. That's not the case. Else, while current node dot get next node dot get value is not equal to value to remove. Let's assume it is. We do the thing inside, but it is in this case. So in this case, adjust the links so that current node. So we have to have at least 3, right? It is in this case. Adjust the link. So current node, this one. Set next node equals current node dot get next node dot get next node. So now this is pointing to this. Then what it's telling us to do is after we remove the node with a value to remove, make sure to set current node to none so that you exit the loop. Current node I didn't think we were in the loop though. I thought we were done. What do you mean set current node to none so that you exit the loop? Set current node. That's what I'm trying to do. Current node is none. This is genuinely one where if I comment out this line. I thought we were done. What I'm gonna do, instead of viewing the solution, is I'm gonna ask my boy, my girl, my dog, my friend, my buddy, my tool, ChatGPT, does this code make sense for removing a node from a linked list? Or is there additional logic that needs to be written? Don't tell me what the additional logic is, if so, but if this is good, tell me. The code you provided for removing a linked list is partially correct, but lacks crucial logic to handle specific cases effectively. This means additional logic is indeed required to make it robust and error-free. Okay, but if I don't care about let's just say, if I don't care about edge cases, is this doing what it's intended? If I have a linked list of 3 nodes and the second node is the value to remove, will this method of a linked list class work? Yes, if you're working with a very specific scenario like a linked list with exactly 3 nodes and you're removing the second node, the provided method will work as intended for that case. Haha. But what about 4? But what about a linked list of 4 nodes? It will also work as intended. So I think that this is a thing of, I'm willing to get the hint, because with my current brain and my current logic, this makes sense to me. So we recommend that you create a variable current next node to keep track of current node's next node. Consider A, B, C again. If A is current node dot get next node is B. If B dot get value is equal to value to remove. So, okay, let me focus. Consider A points to B points to C again. If A is current node dot get next node is B. If B dot get value is equal to value to remove is true, you want to set A's next node property to C. So while current node dot get next node dot get value is not equal to value to remove, current node equals current node dot get next node, but in this case it is, and it says if this is true, you want to set current node's next node, set current node next node is to C, current node dot get next node dot get next node. So this should work. Keep my code and run it. Does your else case traverse the list and remove the node with a value to remove? All right, what are you telling me to do? So current node equals self dot head node is my code. Okay, let me try this. Self dot get head node. Okay. Self dot get head node. If self dot head node. So okay. If current node. Okay. If current node dot get value is equal to value to remove, self dot head node equals current node dot get next node. I mean, it's the same thing. What if I did? Okay, we'll play by your rules. Current node dot get next node. Okay. While current node exists. Okay. I think I gotta brush up on my while loops. But while current node, they did next node is equal to current node dot get next node. So they're saying, right, if we have these nodes, right, what I did was, we're the same up until this point. It was just some like differences in the way we were defining the things, but What I did was while current node dot get next node's value is not the value we want to remove. That's how I did my while loop. Then current node is equal to current node dot next node. So essentially, if we're here and this isn't the value we want to remove, then now we're looking at this one. Now this is the current node. What they did is while current node, so there's just starting a while loop. So while there is a current node that we're on, next node equals current node dot get next node. Cool. This is the next node now. If next node dot get value is the value to remove, current node dot set next node dot get next node. So that we're saying we're setting this next node to our next node's next node, and current node is none. That helps us escape this while loop. Else current node equals next node. Else we assign our next node to the current node. Otherwise we're here. What I did was while current node dot get next node's value is not the value we want to remove, current node dot get next node is the current node. So now this is the current node. Current node dot set next node. So first of all, that doesn't make sense what I tried to do. I tried to do current node dot set next node is equal to current node dot get next node. What I should have done is current node dot set next node. Current node, okay, I see sort of a discrepancy. Is instead of doing this, I should have done current node dot set next node and wrap it in this. That's the discrepancy. Nice. Linked list review. Congratulations, you have implemented a linked list in Python. We did this by defining a node class to hold the values and links between nodes, implementing a linked list class to handle external operations on the list like adding and removing nodes. Feel free to play around a bit with your code. Here's some ideas. Create a few nodes and adding them to a new linked list. Print your linked list out by using your stringify list method. Remove your linked list head node. Print your list again. Was your original head node removed? So far, you've built a method to remove the first occurrence of a given value. How do you think you would remove all nodes that have a specific value? Try building a method to do that. Well, I'm going to tell you something right now. It's 6:45 and it's Ramadan, and the sun goes down in 6 minutes, which means not only have I not eaten in about 12 hours, but in 6 minutes I'll be able to eat, and it's gonna take me a lot more 6 minutes to cook dinner. So I'm gonna peace out, but I feel good about the progress. I do, and I'm gonna pick back up with this soon.